Okay, now that you've created all the materials and the section, we are ready to model the bridge. So let's close that, and I will use a method which consists in first modeling a 2D cable stayed bridge, then to copy these model along the Y direction and link all the elements using the C-beam girders in order to create my 3D model. So to model the bridge, you can simply go into the cable stayed bridge wizard, and by filling all these options, the software will generate automatically the 2D cable stayed bridge for you. So if you choose to generate a symmetric bridge, you only have to define the point A and B position, and it will generate the main it will generate the two parts of the bridge in a symmetric manner. So actually here I will use the default options to generate the bridge. So here you can see the materials I defined previously, the cable, the deck, so I will use the girder material for the deck, the tower, so the pylon here, and the section is also the same. For the cable element type, truss elements are generated, and if cable is selected, it will automatically generate equivalent truss elements for linear analysis, and elastic catenary elements, cable elements for nonlinear analysis. Now I will check this shape of deck option. Here you can choose 0. You can choose 5% for the inclination of the deck, and the main length of the bridge, so the arc length. Okay, if you want the drawing to draw in real time, you can check this option and it will directly draw the bridge in this window. So you see, if you increase the slope, it will give you something like that. So here we'll just choose 5%. Okay, and click on OK, and my 2D cable stayed bridge is easily generated. Now one thing to know is that when you use the wizard, duplicated nodes will be generated at the tower location. So if you look closer here, you see that you have two nodes at the same position. So in order to do the analysis afterwards, we have to merge all the nodes in this model. So go in the node property, select merge, select all the nodes and elements in the model, and just click on apply to merge all the nodes. Now the nodes 34 and 35 were together, now they are merged in one node. Now I will work a bit on the tower modeling. The towers are a bit inclined, and to model that we have to move these nodes on the Y direction of 2 meters around. So select translate node. Here select the option move. Use the selection window to select these nodes, and just choose equal distance -2 and apply to move this node of the tower. Now another thing is that when you move the node, the local coordinate system of the inclined tower element is changed with the movement of the node. So it is actually a built-in feature of the program, but here we want to put all the local axes in the same direction, so we have to change that. First of all, we have to see the local axis, so go in the display mode and element, select the local axis, And if you look closer, you see here the Y direction. Let me make a zoom. You see the Y direction is not in the same direction than here. So we have to click on change parameter, and using the selection option, select intersection line to select this element. Now click on element local axis, change, and we will rotate it off 90 degree in order to align the local axis with the other elements local axis. Now to generate the tower cross beams, we have to divide the tower elements in the z-axis direction using the divide element feature. So go back in this position and we'll go into node, select divide element. Now go in the view tab and again select this intersection line command to select the tower elements. Now here in the divide element work tree, we'll just select frame for the element type, unequal distance. It will be 10 and 36 meter for the division. Check the merge duplicate node and apply to divide the element towers. Now to generate the 3D model, we have first to use the mirror option. So go into this view. Before applying the mirror, we have to move all the 2D model of 7.8 meter in the Y direction in order to mirror it in function of the plane defined by the 0 position. So go into this node element, click on translate, then select all the nodes and elements, select the mode on move, enter the distance minus 7.8 meter and click on apply. So all the elements were moved in this direction. Now I will copy the cable, the main girders and the towers symmetrically to the center line of the bridge. So we have to use the mirror element option. Again, select all the elements, copy, choose the ZX plane at 0 meter. Don't forget to check copy element attributes and mirror beta angle, and click on apply to generate the mirror copy of the bridge. Now we can clear the display by unactivating the local axis, and we'll generate the main girder cross beam. So to do that, click on extrude element. You can go into the top view, go into this option and choose the material girder, activate the nodes too, click on add, close. Now we'll unselect using the unselect window this part of the bridge, and I will extrude the nodes into line elements to create the cross beam between the two parts of the bridge. For the material, use the C-beam girder, same for the section. Use translate for the generation type, equal distance, and here enter the distance between the two parts. So it's 15.6. It's the width of the main span. One time, click on apply to generate all the cross beam. Come back into the ISO view and we'll now generate the crossbeam for the towers. So go in the front view and activate only these towers element using the selection by window and activate. Okay. Now select create elements. So general beam, tapered beam. Select C-beam pylon for the material and the section. Click on this nodal connectivity window and directly on the screen select the element of the towers to link together. Now I will generate the tower bearing by creating new nodes at the tower bearing location. If you make a zoom, you see this part is disconnected, and I will project it on this face. So to do that, again node element, and you have a project option. So select single, and now you can select the nodes which have to be projected. So select also the two nodes on the other tower here. Okay, and select project on a plane and just select the plane, the 3 points to create the plane. Now activate merge duplicate nodes and intersect frame elements and apply to create these projected nodes. Now again we'll generate nodes at the tower bearing using the translate node option. Translate node, select single, select so the nodes you created are ranging from 149 to 152, so you can directly enter this in this window and it will select the 4 nodes you just created. The mode will be copy, 0.27 in the Z direction, and click on apply to generate these nodes. So these elements, these nodes will be used to generate the bearing for the tower. So this model, to model this tower bearing, we use the element link. So go into the boundary window and you have elastic link. So click on add, general type, and now you have to enter the values, so it will be like that. Be careful about the unit. Now we'll copy this elastic link, so it will automatically be assigned to the second tower. So we just have to enter the distance where to copy this. And the two nodes select like that, 1 and 2. And you see the bearings have been generated also on the second tower at the same time. And now I have to activate all, and I will use the same procedure to generate the end bearings of the bridge. So again, use translate elements, translate node, select single, we'll make a zoom here, go back and zoom on this part. Okay. Now that I've selected these 4 nodes, choose an equal distance, z-axis, and we'll generate 2 nodes, minus 4.5 and minus 0.27, and click on apply. Now we have to generate again some elastic links. Boundary elastic link. So same properties, add general type, same coefficients. For the copy elastic link, we have to enter the right distance, which is 450, 54, 15, okay, 414, and clicking 2 nodes here, okay, and okay. Now I have to link these elastic links to the other parts of the bridge. So to do that, we'll use the rigid link this time. So click on rigid link, zoom on the part where you want to assign this rigid link here. Now use add. Here the master node enter 155. We'll use rigid body. Again, I will copy this rigid link, x-axis 220 meter, and you have to select the second node, apply. Now the same for this one, so the master node is 153. Select this node here, apply. Let's see if it has been applied as we want on this part. Yes, okay, it's working. Now let's do the same for this part. Okay, so the only thing to change is here the distance, which is 414, and the master node 159. Now select the node to link it, okay, and master node, and select node 24, apply. Let's see if it has been assigned correctly on the other side too. Okay, seems to be working. Now it's time to assign the support. So click on define support, go into the front view, use the selection window to select the nodes to fix, use the zoom option, again select these nodes, come back, zoom on this part too, okay, now fix everything, the translation and the rotation, and click on apply, and you have so the modeling of the cable stay bridge is over. Next part is very important for cable stay bridge. I will show you how the initial cable press stress is working into midas 7. So it is not so simple to do this, because it is using something called the unknown load factor, and midas civil is actually basing the calculation on optimization technique to find the optimum load factors that satisfy the specific boundary condition for the structure. So we'll use this method to calculate the initial cable pre-stress. So it is a procedure like that in 6 steps. First, the modeling of the bridge, so it's done. The second step is to generate the load condition for the dead load of the main girder and the unit pretension loads for the cables. After that, we'll input the dead loads and the unit loads, the load combination for the dead loads and unit loads. Then we will calculate the unload load factor and using the unload load factor function, and review the analysis results and calculate the initial pre-stresses. First of all, we'll input the loading condition for the self-weight, the superimposed dead load and the unit loads for the cables to calculate the initial pre-stress for the dead load condition. The number of required unknowns initial cable pre-stress values will be set at 20, as the bridge is a symmetric cable stayed bridge which has 20 cables on each side of each tower, and the input loading condition for each of the 20 cables will be input. So go in the load window, click on static load, and here first of all we'll enter the self weight load case, select dead load, add it, then we'll add another dead load which will correspond of the weight of the additional elements on the bridge. So also dead load, add. Now we have to define the pretension cables. So name tension 1, and it will be an user defined load. So cable 1 unit pretension, click on add. Now we have to add 20 times this tension load. In order to do that more conveniently, we'll use the MCT command shell for the input. So it is in the tool tab bar, you have the MCT command shell. The command is stld case, click on insert data, and now we have to copy this 20 times and change the names so to so sometimes it's faster to do like that than to input everything inside the interface. Once the data are entered, click on run, and if you come back into the static load cases, you see the tension loads have been assigned. Close that. Now I have to input the self weight. Choose the self weight load case, -1, add, and specify the superimposed dead loads for the main girder. So static load, beam load element, we have to choose the additional load case, add, uniform load, direction global Z, projection yes, then enter the value minus 18.289. To select the elements, choose material girder add and click on apply to apply the load. Now comes the time at which we have to input the unit pretension for each cable. So we can go into the front view. Here in stamp prestress, click on pretension load, and for each load we have to assign tension 1, and the value will be 1 kilonewton, and I will use the intersection line to select these two elements. So as it is symmetric, I will select at the same time these two, apply, and I have to do that for the 20 tension loads. Okay, now let's go in the isometric view again, and as all the loads are assigned, we can just launch a first analysis. Okay,